Okay, in this video I'd like to talk about how to determine the velocity of some object that's rolling down a ramp. Now rolling adds a little complexity to the conservation of energy. So to just set this up, imagine we have some ramp here and an object, in this case it's a cylinder, begins with some height above the ground. It rolls down the ramp and at the bottom it has some velocity v. Well, when we were in our conservation of energy unit, we had things sliding down ramps, and we said that the potential energy that they begin with, mgh, goes to zero when the height is zero. And although it started with no velocity, at the bottom of the ramp it has velocity, and so we can say that the initial gravitational potential energy would be equal to the final kinetic energy. And so we would cancel a mass and solve for v and work out what the velocity is. But it turns out that's not going to give you the correct answer for a cylinder rolling down a ramp, because there is an additional component to this. Not only is the ball moving, it's also rolling. So there is a rotational component. This component here, 1/2 mv squared, is called translational kinetic energy. But we need to add to that this second component, 1/2 I omega squared, is rotational kinetic energy. So there's two forms of kinetic energy. If this cylinder were just spinning in place, it wouldn't have any translational kinetic energy, but it would have some rotational kinetic energy. And if the cylinder were just sliding down the ramp without rolling, it would be gaining translational, but not rotational. But as it is, this object is both moving and rolling as it moves, and so it has both of these components. Now, if this equation is new to you, let me introduce you to I. This is often called the moment of inertia, or sometimes called the rotational inertia. There's a table in our textbook that has common rotational inertias for objects that you would find. You could look it up and you would find that the rotational inertia for a uniform solid cylinder is 1/2 the mass of the cylinder times the radius, the outer radius of that cylinder. So 1/2 mr squared is what we would put in for I in this problem. Now another substitution that's going to make our life easier is to recognize that omega, which is the angular velocity of this, it's how many radians per second this wheel spins, that omega happens to equal linear velocity divided by the radius. This would be in radians, meters per second, and meters. So I'm going to now substitute those in. Let's see what we get. Zoom in here a little bit. Now substituting for the moment of inertia, or rotational inertia, that's 1/2 mr squared. And for omega squared, that becomes v squared over r squared. Now this is great. You can see that a lot of parts, a lot of variables will drop out. I can divide out a mass from every term, and I see that there's a radius squared up here in the numerator and a radius squared down here in the denominator. So let me write that. I have 1/2 of a half, so it's going to be 1/4, and the r squared's canceled, the m's gone, so I simply have 1/4 v squared. Look at that, that's great. I can easily find this velocity now, because gh equals, what is that, 3/4, find a common denominator, v squared. Or if I solve this for v, v is square root of 3/4, square root of 4/3 gh. Right, I would multiply both sides by 4 and divide both sides by 3. Okay? And what is that? We get a velocity of 5.1 meters per second. Now, if this cylinder slid down a ramp without friction, because there was no friction, there would be no force to cause a torque, and without torque, the cylinder wouldn't roll. So if the cylinder slid down the ramp without friction, it would reach the bottom with a greater velocity than 5.1, because all of its potential energy would become translational kinetic energy, and so this V would be larger. However, because there is friction, and that friction pointing backward creates a torque on this cylinder, the cylinder would roll, and as it rolls down, it does gain velocity in energy in the form of translational kinetic energy, but it also gains rotational velocity. I'm able to put those together and solve algebraically for this velocity. You could work out what percentage there is. In fact, in this case, because I have a half v squared here and 1/4 v squared, of all of the energy that we begin with, which would be the mgh, that would be split up amongst the 1/2 and the 1/4. And so you could work out the percentage. What does that mean? That this would get 1/3 and this would get 2/3 of the total energy? I think that's right. So you can work out percentages that way. Either way, we use an expression like this to find the velocity gained when rolling down a ramp.